Hi, just one more set of examples from 11.2. We have lots of nice results about random variables and summing them now. And I'll show you a few more of them, but there's many more you could prove now. That there's a sheet I think you might not have downloaded, but just the relationship between all these random variables. And when you start summing them, this is actually a very intense computation. You can get very interesting results. So actually moment generating functions is very helpful for us to see what should be happening when sometimes these things like by hand are almost, well, I wouldn't say impossible to do, but very time consuming. The next very nice result is that the sum of independent Poissons is Poisson, which kind of makes sense. I mean, if you expect so many errors per page in one book and so many errors per page in another book, if you put the two books together, you would expect the sum of the amount of errors per those two books. So I don't think that's it's a surprising result, but we have to show that it's true. And if just to do it outright is quite hard, but using moment generating functions is nice. So how do I do this? So I don't know. I'll do it for, I guess I'll just do it for general n random variables. So let x1, x2, x3, xn be my independent Poisson random variables. And so let's look at the moment generating function of their sum. So this is just exactly what we did with the normal. So this is the product of their moment generating functions. N of t, this should be x2. So now I have to remember the moment generating function for a Poisson, which of course I must admit I do not memorize everybody's moment generating function. This is e to the lambda e to the t minus 1. So this is e to the lambda 1 e to the t minus 1. I'll let lambda 1 be the parameter for x1, lambda 2 for x3, lambda n. Okay, so this is times e to the lambda 2 e to the t minus 1 times e to the lambda n e to the t minus 1. Product of a bunch of exponentials is exponential. I sum their exponents, so lambda 1 e to the t minus 1 plus lambda 2 e to the t minus 1 plus lambda n e to the t minus 1. This is equal to e to the, I can pull out all the lambdas, lambda 1 plus lambda 2 plus lambda n times e to the t minus 1. And this is the moment generating function of a Poisson, where this is the new parameter. So x1 plus x2 plus xn is Poisson with parameter lambda 1 plus lambda 2 plus lambda n. That's a very nice result. And so, for example, suppose that, and here's an application of what I'm saying in case this, like why would this come into play? Suppose x and y are independent Poissons. They both have a mean of 2. What's the probability the sum of them is bigger than or equal to 3? So here's just an application. Let x be the number of calls Dr. Grimaldi gets in a day. Let's say that number is Poisson 2, and y is number of calls I get in a day. Let's say that's Poisson 2. What's the probability on a random day that together we get more than 3 calls, where I expect him to get 2 calls per day, you expect me to get 2 calls per day. So on average, actually, if you add the number of calls we have together, that should be Poisson with a lambda of 4, right? Together, if he gets 2 per day and I get 2 per day, then together we should get 4 per day. So what's the probability then that a Poisson is greater than or equal to 3 when we see actually on average we should be getting 4? So I'm just going to sum a Poisson. Poisson is discrete, so this is e to the negative 4 times 4 to the x over x factorial. I probably shouldn't have used x. That's not really good, right? let's call this new random variable W. Well, so probably W is bigger than or equal to 3. That would make this W, that would make this W. And W, I'm going to sum from 3 to infinity. Okay, nice. Another nice result, sum of independent and identically distributed binomials with the same probability P is binomial. Sum of binomials is binomial as long as you have the same parameters. So let X be the number of free throws I make out of 10, and let's say I have a 70% chance of making a free throw. Let Y be the number of free throws that Dr. Yatesai makes out of 20, and let's say she's also a 70% free throw shooter. Together, if you, let me see, if I'm 70%, you expect me to make 7. If she's 70% and she shoots 20, you expect her to make 14. So together, the number of shots we make together should be binomial with, let's see, together we're shooting 30 shots, but our probability of success is 0.7. So what's the probability combined we make, what's the probability that combined we make at least 25 shots? So what's the probability combined we make at least, so 25 or more shots? You would expect us, actually, if we shoot 30 shots together with 70%, we should make at least 21. So I'm just going to sum, let's call again this W. Let's sum W from 25 to 30. Let me see, this is 30 choose W, 0.7 to the W, 0.3 to the 30 minus W, and just sum that, maple something. Okay, and there's lots of other nice facts. I just gave you some. Sum of independent geometrics is negative binomial. This is the number of trials till the first success, and this is the number of trials to the rth success. So if you sum geometrics, it's not surprising you get negative binomial. Sum of negative binomials is negative binomial. Sum of independent exponentials is gamma. Sum of independent gammas is gamma. So we haven't discussed the gamma, but there's not, I mean, and people come up with these through looking at their moment generating functions. And the sum of a large enough, if you sum a large enough number of any independent random variables, you're going to get back to a bell-shaped curve. And I have some really nice videos showing that. I think I'll save it for the next video because I'm still waiting this exponential one. I've been having it run for about an hour or two now to find the sum of 10 exponentials. This is, like I said, this is not easy stuff. So I think it's only summed 5 of them so far. So when I go to the convention tonight, I'm going to let the sum the rest of them. So by the time I get back, hopefully you can see the sum of exponentials is normal. I'm doing this, running it right now in Maple, and it probably needs to run the rest of the night before I'm done. So I'll show you that in the next video. It's just a nice little thing. And then if you want any more examples on this, I do have this in homework set 7. I've a couple places where I summed random variables, but if you need any more help or you want to see another example, just let me know. And I will post the other stuff later once I convert.